the wonderful Slang, continuing on with his quantization of gravity, although this time I think with a bit of Q&A towards the end.
Yes. Thank you, Bubs. It's true. Today we will summarize a bit of stuff from the last ones, but then in the end, I hope we can just like do Q&A, do a bit of discussion, outlook, all that jazz. I was thinking of adding a bit of Quantum Cosmo stuff today, but I don't know. Maybe for another time. Maybe as a little supplement PDF or something. Because I just tried the calculations today and they were not working out. Turns out doing all your research in advance really and making the notes way in advance is a great idea when your notes are as messy as mine. So yeah, recording is started. Everything's ready. Great. Then yeah, today's a bit more lenient. I just want to start with like a bigger section on what we understand are the problems we face in quantum gravity. Not necessarily just quantization of gravity, but QG more generally. So these are supposed to be things that give me give me uh, alrighty. So where were we? Yes. So this is meant to be about QG stuff in general. So to recap what we had so far, we saw how to take GR and using the ADM formalism split it into time-like and space-like parts, and also how to do the whole Hamiltonian analysis on it and extract from it the physical degrees of freedom of GR, which we saw were 2 degrees of freedom per point, which tells us there's some sort of analog of a graviton also at the non-perturbative level. Then also we understood that imposing the constraints of GR, so the Hamiltonian constraint and the spatial Diffie constraints includes the dynamics of GR, but also is a hallmark of general covariance. Now, in principle, therefore, we know what to quantize, and we've also seen how to construct, in principle, observables on the phase space. So we also kind of know what the observables of GR are, or at least we have an idea of what they look like. So really, then, what's the core issue? If we have all of these things, then it can't be that difficult to produce quantum gravity, right? So the answer is, of course, no. It's not that easy. But the reason for that is it has like many different aspects. So the very first one, which I want to get out of the way, is the technical stuff. So say you want to really stick to the ADM formalism, which is this very old school sort of approach. Then you have the issue of actually constructing a Hilbert space. So it's not enough to just take the operators and put hats on them and realize the momentum as a derivative and the position as a multiplication. That's not enough, because in the end, what you need is some sort of way to take scalar products of wave functions and a way to extract probabilities from that, and also have enough control over what the operators look like and how to evaluate stuff so that you can actually calculate things. So for example, if you work off-shell, so you don't impose the constraints at the classical level, but at the quantum level, then you first have to figure out how to make a Hilbert space of metrics. And that is pretty difficult, because the space of metrics is a very complicated manifold, infinite dimensional, and it doesn't really have any nice properties by itself. In fact, it's barely known what this space looks like for most 3D manifolds in the first place. There's some literature in mathematics about this, but it's complicated. It's a very, very complicated space. So it's already difficult enough to imagine studying the space by itself, even if you just want to use coordinates. But even worse, you have no idea if you want to realize it as a sort of like wave functions where you integrate over stuff, then what the hell is the measure of the integral going to be? And this is not a path integral question, mind you, because we're not doing path integrals here. So it's not that you have no idea how to construct a path integral measure, which would be the usual problem. But it's also not clear how to write something as simple as, say, dx psi x phi x. So the corresponding thing that you would have in single particle quantum mechanics. So the question is, how do you construct this in the inner product? That's not clear. And even if I just gave it to you as a symbol like this, how would you evaluate it? If I give you some functional of metrics, how are you going to practically evaluate this? It's not really something that you can just do all the way just using symbolic manipulations. You need at some point something concrete. You need something like an exactly solvable subset that you can maybe do perturbation theory around. But in principle, you just need something concrete enough to actually start calculating stuff. And this is technically difficult to construct. In particular, what's difficult to get for this canonical approach is not just the measure itself, but also its symmetries. It's known how to construct measures on certain other spaces which have invariance under spatial diffeos. But the time-like pieces, the time-like invariances are very, very difficult to implement. So overall, it's technically very challenging. The second thing, if you do it like this, is when you have done that, once you have a Hilbert space, how are you going to make the constraints? Because there's the usual issue of that you need to write down a preferred ordering of all of the operators, because the classical theory does not give you that. And this already appears in the very simplest cases, even when you just look at something like cosmology. There it's already ambiguous how to write down the constraints. But there's also the issue of having of writing down the constraints at the quantum level, checking their commutators, and it doesn't match the classical Poisson brackets. That can happen, and that's what's called anomalies. And overall, it's really just a mess of a thing to implement. There are some successes in regards to this coming from different approaches to canonical QG, but in ADM, this is basically as hopeless as it gets. Okay, Babs asks, are you holding the space-time topology fixed when you're discussing this measure? So if we're still in ADM, then yes, the space-time topology is still globally hyperbolic, and the spatial topology is also fixed. Now, for going past the semi-technical stuff, past the technical stuff, there's some semi-technical stuff, so it's a bit more about conceptual things. We already had the initial restriction about having only positive lapse functions. What this was for was that we needed future-directed foliations, so that time only flows forward. In a way, this means that we are completely ignoring the question of the arrow of time, which, okay, we don't have to deal with it per se, but it kind of opens the question of how you impose that on the quantum level. For example, in a path integral, it's going to be difficult to do that. And also, if you include all values, just even in this canonical setting, you have a problem. So say you are in the path integral, and you say you have a measure already which takes care of the symmetries of the canonical theory for Q, But you still have this, you still have the labs flying around, and you want to integrate over it the same way you would usually do in a path integral. So there are some gauge parameters, and you can gauge fix stuff, but you will still integrate over it. The main issue that emerges from this is that if you only have a positive lapse, then everything is fine. You will only get exponential, a complex exponential. But if you also include negative values of the lapse, then you actually end up with a cosine of whatever action actually works for gravity. This is called the cosine problem. And if you want to go past the purely canonical approach, where you have only the positive lapse functions, then you have to face this problem. So in general, making a step from canonical to path integral is less problematic than starting from a purely covariant path integral in GR, because somehow you need to argue why you restrict your lapses in such a way. And if you do not, then you have to argue why the cosine here somehow becomes a complex exponential again. Now, the next thing is that it's actually pretty difficult to construct observables that you can actually compute and compare with regular GR. So the classic thing that people check in GR that tells you that there's, for example, a curvature singularity is the Kretschmann scalar. So for example, you could take the 3D Riemann curvature tensor, take the Kretschmann scalar of that, and just integrate it. And then you could, for example, take that as a function of the total volume of the slice. And then as the volume changes, you get an observable that evolves with time. That would be one case of an observable. And there are many, many different things you can study with this. But if I write it down like this, it should already be clear that this is a pretty complicated object. And if I were to now invert the first of these functions for the second, so that I have a Kretschmann scalar as a function of volume, that's going to be an even more complicated function. So in principle, we know what observables must look like, but they're still very complicated and therefore hard to construct once you actually have a quantum theory. They're just very complicated things. And there's not really like a simple way to write them down. So let's move on to some more purely conceptual questions. The biggest thing in the room, I would say, is that if you want to do QG, you would need to test it on something. And apart from the obvious cases of strong field gravitational physics, which means black holes, neutron star mergers, cosmology, maybe something like cosmic string defects, it's unclear how much you will actually need full non-perturbative QG to study the other cases. So of course there's some ways to study those in a much more simple way, although you can argue whether that is perfectly fine in general. A simple way would be to just look at the data of black holes classically, or of cosmology, and just quantize that, which would be something that people call symmetry reduced QG. So you literally just look at the data and for example, the scale factor and some scalar fields, and you call that homogeneous cosmology. And then you quantize the action that you get from GR from this, when everything is homogeneous. This is a very big field of research, actually, and people can extract a lot of interesting stuff from it. In particular, they can make predictions about inhomogeneities in cosmology, and also about singularity formation. And in black holes, there's also some interesting research recently in the same vein. But the kind of question is, does this really match what you're going to get if you use full quantum gravity? Or the other way around, do you need full quantum gravity to study those cases? Or can you just look at some more simplified sort of semi-toy model thing? And the answer is we kind of don't know. We cannot know because we don't have a fully exercised theory of QG in which all of this can be perfectly controlled, and we know if there's like influences from other sectors that change what cosmology looks like. But overall, you can sort of see from this, okay, if you want to talk about QG, is there anything you can talk about that is not black holes and cosmology? And as you may know, black holes and cosmology do get a lot more experimental verification recently, but until recently, that used to not be the case. Particularly with black holes and with gravitational waves, until like 10 or let's say 15 years back, there was nothing that you could very directly observe. And without that experimental evidence, it was difficult to imagine where you could even apply or test quantum gravity, full quantum gravity. There's one thing that I want to add to this little list here. No. There's one little thing I want to add, which is if you are not so keen on, say, relativistic high energy, so instead at low energy, you can still just do something like superpose masses. And if you superpose masses at different positions, then you're going to have a superposition of at least the Coulombic part of the gravitational fields they produce. So in that sense, you can do very simple QG experiments in a lab, which people nowadays refer to as tabletop QG. So you can do this. You can definitely do this stuff. And it is a valid test of quantum gravity in that you will have quantum effects and gravitational effects. But do you really need full non-perturbative QG for this? And this is not so clear. So one of the issues of non-perturbative QG is that some of the experiments may just not be sensitive to whatever you have at high energies in the first place. And it's maybe easier to just look at perturbations of flat Minkowski space time just at low energies. Now, the next thing, if you have a more realistic model, which includes quantum gravity and other stuff, then matter must enter on a similar footing as the rest to construct some observables. So you can no longer really speak of stuff in the same way that you do in classical field theories or say in quantum field theories where you just have Minkowski space in the background. So you no longer can just speak of, I don't know, having scalar field values on M at a given point. You cannot longer evaluate the value of a scalar field because you now need to specify things in a way that puts everything on even footing. You now have dynamical metrics, and everything needs to be dynamical. So if you want to do for example, a free theory and perturbation theory around it, as you would usually do in quantum field theory, then you have the issue that in principle you don't really know what you're going to perturb around. Because gravity, GR, is not something that you can write as a free theory. So if that thing does not admit a perturbation theory and not an exact solution, then what are you going to perturb around? Now, on top of that come the general, usual hard to ask questions of QG. For this, I would like to invite you to a game of Taboo and try to do physics without using ideal coordinates, time, so you don't have anything like unitarity. Try to do it without space-time symmetries. Good luck defining what a particle is without this. Also, try to do that without points. You can no longer say where you evaluate a scalar field. Where is a point? What is a point? And good luck talking about causality when your metric can be literally anything. So how do you know what a space-time causally propagating field theory is, or a particle that's propagating causally, on an abstract level, on a general level? How do you write that down when you have a general theory of QG? These are things that if you want to write down a most general theory, so a full theory that includes everything, you're gonna have problems. You're gonna have problems, and you're gonna need different vocabulary and different expressions to ask similar or perhaps new questions. So it's no longer going to be as easy as I calculate some scattering of particles coming in from very far in the past and going out very far into the future, and I evaluate them by using some expansion around a non-interacting theory. It's not going to be as simple as that anymore. Now, the general theme of this is that all of these notions need to be provided dynamically. So similar as you can know, so I want to give you a small analogy, which is like if we have a theory of point particles with charges, then we can ask something like, okay, in a given electromagnetic field, they are going to experience such and such a force. And they are going to move like this and that. Now, if I make electromagnetism dynamical, then I know I start with some initial configuration, and then the particles move and they eject some electromagnetic radiation and so forth. But still, at any given point in time, if I have some knowledge about the initial state of the electromagnetic field, I can just answer the same questions as before. This is different if I now want to do quantum electrodynamics. I can no longer ask something as simple as I want to calculate, say, the quantum corrections to a given classical electromagnetic field configuration. How do things behave in a cylindrically symmetric electromagnetic field? That's not going to be something you can just calculate using the regular path integral. You're going to need to modify it somehow. You're going to need to somehow introduce some change to the path integral so that what you calculate actually gives you something close to the classical calculation. By itself, the path integral has all field configurations in it, and you can't just pick out one. You can't just pick out one and some small corrections around it without also the other ones influencing what you calculate. That's something to keep in mind as an analogy. One way to extend these these prescriptions for QG, one that will absolutely be necessary in order to speak of time and such, will be to have at least some notion of a clock system. So you could have some ideal clock in the system that has basically no energy, no momentum, and so forth. Or you could use the global volume as a notion of clock in cosmology, but good luck doing that if you're just in a laboratory frame on Earth. Now, the next thing, purely conceptual again, is about interpreting the amplitudes of QG. So I already spoke last time about ways you can interpret them, for example, as Schrödinger states, so they don't time evolve, in which case you don't need to wonder about, okay, like, why is there no, if there's no notion, if there's no time evolution, then what do the states mean? Well, what do the states mean in Schrödinger? What do the states mean in the Schrödinger picture? They're just data. So what you can do in general is interpret these amplitudes in a conditional way. So as conditional probabilities once you square them. So because there's no preferred clock, you will not have any idea what a measurement at a given point in time means. So instead, what you can do is discard time altogether and use just probabilities. But who is calculating those probabilities? Who do they pertain to? And how do people know about the probabilities? So this is sort of a question about whether you interpret these probabilities, in which way you interpret them. Of course, in addition to that, you can introduce a notion of time through several options, but all of them, say, as a physical clock, will allow you to say, I condition my probabilities on the given value of the clock. So I can calculate the value of the chance of getting into a state at clock time 2, conditioned on the state that I have at clock time 1. And then you can ask the usual questions. So you can ask, is there a unitary time evolution of these probabilities or the amplitudes, let's say, with respect to those physical clocks? Then next, you need some sort of notion of locality, which also lets you address questions of causality, as raised before. If you find a way to localize events or regions in a way that is independent of having coordinates, then you can address all of those questions. But more generally, if you don't want to do that, if you don't want to fix everything on a given notion of clock, or like your interpretation should be independent of whatever choice of clock you make, then there's still the option of interpreting the probabilities as Bayesian. This means that you see the probabilities as encoding a degree of belief that a certain event will take place or that a certain property will hold true once you perform some sort of check on the property that you want to check. And these degrees of belief are always conditioned on what initial information you have available. So by itself, you can do this even regardless of whether you're doing QG or not. Are we having connection issues? Thank you. Okay, recording continues. Okay, yes, so you can also do this in regular QM. There's in principle nothing about QM that requires a notion of time evolution. You can just have a Hilbert space and some operators, and you just don't have to evolve anything. It's in principle not a part of the formalism that is this okay? Stream unpaused. We had some technical disturbances, but we are back on track. All right. Yes. So in QM, in principle, you also don't need a notion of time. So this Bayesian probability interpretation is also an option there. And therefore, you can just work with it the same way as usual. You can just see quantum mechanical probability amplitudes as encoding some sort of degree of belief about the state of a system. If you go through with that, then you have in principle no issue with interpreting quantum gravity. And you do not need it to introduce some notion of clock or time or observers or whatever. Okay, further small technical difficulties aside, now, in principle again, you can just proceed with interpreting the amplitudes regardless of whether you want to introduce a clock or not. Now, for some advanced problems, this will be just the part before the outlook. You can go beyond global hyperbolicity if you want. So the comment about space-time topology was adequate in that so far we've only been working with space-times that have a clear time evolution going on. You can change this. You can go beyond this. The first is that you stay in the Hamiltonian picture via what's called the covariant phase space. What this is instead of looking at sort of initial values, which would give you the canonical phase space, you look just at the full set of solutions of the equations of motion. Which gives you the covariant phase space. Now, for good theories, if you have something like an initial slice, so you have an idea of what initial values mean, then these two should be equivalent. So in principle, we can take the whole formalism we had so far, which was the canonical phase space picture, and we can just transfer all of the results to the covariant phase space formalism, where you still have a notion of symplectic structure, Poisson brackets, and so forth, and do the same things. Just that now we're working on a general space of solutions, and in principle, that does not know about any time slicing. So if you do it with that method, which is more advanced, then you don't really need to restrict to globally hyperbolic theories. Then instead, you have a more interesting question of how to construct path integrals, because now you're working with space-time configurations. So it sounds like it's much more obvious to construct a path integral. And as far as I'm aware, it basically just consists of having a phase space path integral. So you integrate both over positions and momenta. Now there's also the option that comes from this, that now you do not longer have to restrict yourself to spacetimes that have a fixed spatial topology, but you can also have something like where you start with an initial slice, and then through some complicated spacetime, you end up with a final slice which is disconnected. So that's what people call a topology change in quantum gravity. That's something that is established to be possible to do in 2 plus 1 dimensional gravity, so 3D gravity. In 4D, it's known that classically there are solutions which do this, but it's not so. But it's, for example, not possible if you do a simple canonical phase space analysis. So there are some caveats to whether you include this. Some people say it's absolutely necessary. Some people say it's not necessary, and other people say it's not. It shouldn't be there. In particular, if you want to work with general theories of these four-dimensional manifolds, then you have the issue of dealing with all the different types of topologies and how to sum over them. And you're going to run into several issues. In particular, that you're going to run into the issue that you cannot simply count or sum over four manifolds. Not algorithmically. What this means in practice is that, say you want to write down a path integral and sum over all possible topologies, in addition to metric data and such. Then you're going to want to write down some sort of sum over different topologies. The sum will have some sort of index set, and this index set should uniquely enumerate some manifold. Otherwise, you have no real control over what is going, like how many times you're actually counting a given topology. But in order to do that, you need to somehow have a set of numbers or at least some prescription by which one term in the sum is uniquely identified as having a given space-time topology. This is known to be impossible in general. So it's known, for example, that just by what's known as the fundamental group of a four manifold, you cannot do this. You cannot find an algorithmic procedure, so say an enumeration by numbers, which tells you, given these numbers, I get a manifold with this fundamental group. So in principle, you cannot enumerate four manifolds. That's one way you can say it. And this is a problem that you have to deal with in the end. So somehow you need to organize your, if you want to do a sum over topologies, you either need to restrict to a set where you can actually perform a sum, or you need to somehow deal with the fact that if you use smooth manifolds, smooth is the key word perhaps, you cannot enumerate them. And so the sum over topologies is not possible. Now, if you want to do something more classically attuned, if you include all of these spacetimes, then you have the additional question of saying, okay, what if I want to do quantum gravity on Minkowski spacetime? Then you somehow need to identify from the path integral some specific subsector, which corresponds to only the contributions where the spacetime has a given topology of Minkowski. That is even more difficult, and it's an additional problem you have to face if you include these more fancy topologies. In principle, for example, it's known that if you just write down a generic theory with these sorts of topology changes, then the dominant contribution will be from something that has the topology of de Sitter space or anti-de Sitter space, depending on what you choose for the constants. Often I think they get de Sitter space actually. And this means if you want to get Minkowski predictions, or for more specific space-time topologies, or more fancy ones, then you're going to have to do even more work to ask questions about that. And that's already independent of whatever paradigm for QG you were trying to follow here. So that was my small and very inexhaustive list of problems in quantum gravity. So I will now go to an outlook in which I will speak more loosely about some features of QG, some cool stuff, and also about a small list of contemporary approaches. In that, I will give you the dreaded QG political compass. And at the end, we can have some open discussion. So, to start, some cool features of QG that I want to point your attention to is that because of its symmetries, it possibly acts as a regulator, a natural regulator for high energy QFT. So an issue in QFT is that you have divergences. You have loop divergences because in principle, whatever you calculate has contributions from infinitely high energies, and those infinitely high energies will make everything diverge. So what you need to do, regardless of how you interpret that, is you're gonna need to regulate your theory. So there's going to be some kind of way to make everything finite. What's known about QG in general is that it typically acts as a sort of regulator. In string theory, this is very well and elementarily known from worldsheet calculations, in that when you look at worldsheets of string theory and compute amplitudes, then the first few things you can calculate already very explicitly. The higher ones are more complicated, but what's known is that the ones that we can calculate are actually finite. So you can see these sorts of higher genus worldsheet calculations as being refined versions of the loop calculations you do in quantum field theory. So you take a loop diagram, and you stretch it out into a worldsheet of a string, and then you find that the string theory result is finite, whereas the QFT result is infinite. So this is one way by which you can see QG regulates loop divergences, for example. There are other approaches in which it works differently. For example, in loop quantum gravity, which is another canonical QG approach, but using different variables, you have that there is discrete spectrum of eigenvalues for geometric operators, for example, for lengths, for areas, for volumes, and for angles as well. And this means that, for example, the momenta in loops will also have discrete or even finite or even bounded spectra. So these also regulate loop divergences, although the connection is not as direct as in string theory, where you can just take the string radius to 0 and then you get a loop diagram. In QG, you have also ways to do that, but there it still just comes down to the fact that you have finite values of everything on each link of a Feynman diagram. This is also done in other approaches which are discrete. For example, in the causal sets approach, it's very similar, and in causal dynamical triangulations as well. There's also, I think this is the most direct way you can convince people of this general property if they only like continuum QFT. You tell them about the renormalization group flow of Einstein-Hilbert theory plus some theory like QED or even the standard model possibly. this will tell you about how what a theory looks like at high energies and at low energies, and if the theory is well defined to all energies. And what's known is that if you, for example, take Einstein-Hilbert and QED, then there is a well-defined theory up to all energies, up to all high energies, by virtue of what's called asymptotic safety. So there's a sort of changing of the theory as you go to higher energies. Parameters adjust depending on the energy a little bit, and you find that QED by itself does not have this. QED is not well defined to all energies by those measures. But if you add the Einstein-Hilbert action to it, then it works. This is probably the most direct way because it doesn't use any fancy new technology. It just relies on renormalization group analysis. And in the end, it seems that it mostly comes from the fact that GR or Einstein-Hilbert or ADM or whatever have a set of symmetries which are restrictive enough to make the theory mostly finite. There's a question by Babs. What do you mean Einstein-Hilbert is possibly well-defined to all energies? Having gravity means you can't do perturbation theory. Yes, but that just means you have to do an RG analysis, which does not do perturbation theory, which you can do by way of functional RG. By the way, this is not something you just can do with like Einstein-Hilbert. You can do this sort of analysis also for the standard model, just like that, and with Higgs, extra Higgs fields and so forth. And this is like a way that people can predict the Higgs mass or like bounds on the Higgs mass. So these are things that you can do very generically in whatever QFT you want to study. These are perfectly standard methods. Yes, absolutely. Yes, so Bab says, you were saying functional G can be done for non-renormalizable theories, and that'll tell you something about being well-defined. Absolutely. I have no doubts about that. Functional RG, non-renormal makes it not well-defined, though. I wouldn't say so. In principle, all it tells you is that you need infinitely many counter terms. And functional RG as a method does not make a distinction between the two types. Yes, but the thing is that if you have a well-defined functional RG flow from UV to IR, then you know all of the theory at all energies. Then you know what the couplings are like. Then in principle, what you have is the quantum effective action with all of its couplings at all energies. And you know that in the UV, all of the couplings achieve a finite value. Yeah, well, I mean, in principle, you're gonna have to like truncate it to some manageable amount of couplings, but that's more of a practicality issue. If you can do 10 billion couplings and do the analysis, then you have 10 billion couplings. Then you're doing EFT. Well, I mean, but that's the same thing if you have just renormalizable theory. Then you're also truncating everything to just have the renormalizable couplings. But by excluding gravity, yes. But I'm telling you that if you do it with gravity, you can do the same method, and it gives you the same criteria as you could do in EFTs or in whatever you want to call a theory that has finite couplings at all energies. Like, what's important here is really the fact that the couplings stay finite at all energies. That's what is meant by asymptotic safety. If the couplings become infinite, then you're out of the realm of even talking about a well-defined theory. It's the usual notion of RG. What do you mean? I mean, it's a typical case if you don't have a well-defined theory to all energies. Okay, you know what? Let's get back to this in discussion. Babs. Okay, now the next thing is, okay, saying non-precise things is also part of the fun here in it. Now, what seems to be happening in a lot of these quantum gravity theories, by mere chance really, is that you have some sort of effective space-time dimension. So what is meant with this is that, say we do ADM quantization, then of course the space-time dimension we start from is 4. There's no question about that. And this dimension that we set to 4 is what we call the Hausdorff dimension. So this is a measure of how a ball in the space-time scales in volume once you change the radius. So the balls in the space-time that we look at will always have a given fixed Hausdorff dimension of 4 if we do it this way. But what's known from bottom-up approaches, where you don't start from a 4-dimensional, so like some coordinate ball, just having a sort of, so the question was what sort of ball? So just, I don't know, in 3D, you fix some radius, and then you take the coordinate ball where the squares of coordinates are given by and are less than the radius squared. So that sort of ball. Now there's another notion of dimensionality, which comes from the theory of random walks. So this is sort of what you can study if you have actual particle propagation on the spacetime. It asks, if I take a particle and let it walk randomly across the spacetime, so it can change direction randomly and change momentum randomly by a Gaussian distribution, then I can ask, okay, there's sometimes the particle goes in a circle and comes back. And it takes a certain time for it to do that. So what you can then do is ask for the return probability as a function of time, of return time. And this allows you to then define the notion of spectral dimensions. And what's known from a few approaches, particularly from asymptotic safety above and from causal dynamical triangulations, is that at low energies, which has a certain meaning in those contexts, you find that the spectral dimension is 4, but you will also find that at high energies, again, this has a certain meaning there, the spectral dimension is 2. So what you receive is that at high energies, you have what's called dimensional reduction. This is more specific to the different approaches. For example, in string theory, it's usually asserted that instead you have dimensional expansion. So you have instead something like 10 or 11 or 12 dimensions. But in some theories, you also have dimensional reduction. Overall, though, what definitely comes out is a picture where space-time dimension, depending on the notion, can be effective, so can depend on the circumstance. Now, there's also a general feature of QG which addresses some typical classical questions. For example, there's a number of black hole paradoxes, like the black hole firewall paradox, information paradox, cosmic censorship conjecture, etc. pp. And basically, depending on the approach, you will have at least 5 resolutions to whatever black hole paradox you can think of. At least 5, because typically it's not unique how you write down a black hole and how to correctly address the corresponding paradox usually also has different ways. There are different answers, different interpretations. So you will not usually find a unique answer. So what should be clear from this, perhaps, is that there's not necessarily it's not enough to ask for it's not enough to ask for resolutions of these paradoxes. You need more stringent criteria to signal out a QG theory. Now, with regards to cosmology, there are many different approaches to this. Some are directly inspired from big QG approaches. Some are more phenomenological. Some are more toy models. And I'm not going to get into details on this because this could be easily its own talk or its own series. If there's interest in that and if I actually get more acquainted with this stuff. But you should keep in mind about this that the main 2 areas of strong gravitational stuff, so cosmology and black holes, get addressed in many different ways by quantum gravity as an overarching field. Now, let's get to the fun part of the talk. The quantum gravity political compass. So, I've drafted on this a little list of approaches which I have graphed depending on how sort of conservative they are, by which I mean how many like additional things do they add, how far does it deviate from GR, let's say, from the predictions of GR, and also by how closely they are to the continuum. And there's a sort of dichotomy here, which is maybe also a false dichotomy, between staying completely with continuum data or with discretizing everything and somehow getting continuous space-time out of discrete building blocks, sort of an emergent continuum space-time or space. And I'm going to go through a few of these approaches to give you an overview. The first, which is, I think, closest to what we've discussed so far, but okay, just denote here that ADM by itself is also on this list. So quantized ADM, I would describe as the most conservative theory because it's literally just GR. and also as purely continuum, because there is no restriction on sort of, or discretization going on whatsoever. Then another one which is relatively close to this is loop quantum gravity. This you can think of as canonical quantized GR, but with different variables. In tetrad and connection variables. So this is very similar to lattice gauge theory stuff. So the reason that I put this near like the conservative end of the spectrum is that it really comes directly from the canonical point of view. And it also has this sort of fixed spatial topology and continuous time evolution. And it really only changes the variables and sort of uses a different representation of the data in which you can actually proceed more into the technical details. Then I also put it on the more discrete end of the spectrum, but not all the way, because it's not quite fully discrete. What it actually is a continuum approach, where if you decompose the basic Hilbert space into into basis states, then those basis states are constructed from embedded graphs. So you sort of classify the Hilbert space of states by discrete data, but these discrete data still correspond to continuum configurations. And only depending on how you interpret things and how far you take the sort of picture of having elementary building blocks as being true building blocks, depending on how you interpret that, you call it more discrete or more continuum. But it's definitely true that this is a continuum approach, because you can get continuum statements from it. Now, there's a second approach which stems directly from LQG, which I've denoted here as spin foam models and as group field theories. So first, about spin foam models. Those you can basically think of as discrete path integrals in the variables of LQG. So it's discrete lattice path integrals. Same with the same states as LQG. This is for fixed discrete spacetimes. But once you resum over all topologies, you get what's called group field theory. And the picture of group field theory is very rich by itself. One could sort of say that it's an auxiliary field theory. Where the Feynman diagrams are spacetimes. But discrete spacetimes, of course. So this I place, these two I place more on the discrete end of the spectrum than LQG, because they are by their definition about discrete data. How to get a continuum out of this is an open question, in the sense that you need to address it based on the starting point that you get it from. It's not like in LQG where you know how to get the continuum ab initio. In spinform models or group field theories, you have to tell which regime, which way, which limit you have to take so that you get something continuous. I also place them further in the expansive direction, so further deviating from GR. In particular, because spinform models definitely allows you to include topology change. And group field theory, by its nature, requires that you sum over topologies. That's just a few of the reasons why I place them like this, but that's some of the stuff. Next, we have string theory, or by its bigger, more ominous name, M theory, which I'm going to summarize as GR plus standard model coming from a low energy effective theory. In 10 or 11 dimensions. SGR plus standard model. Well, I mean, it's just saying that this part of what we call that is a low energy EFT coming from string theory. I'm not saying there's nothing else coming from string theory. Like, there definitely are like many, many more degrees of freedom in it. There are many additional fields, many additional degrees of freedom, many geometric details. In particular, particles, space-time, etc. are special cases, or well, let's say limits of special cases, like the point particle limit of a string gives you a point particle of branes. So geometric objects, so some submanifolds which are embedded in some 11-dimensional spacetime. Its completion, which also makes the 11-dimensional spacetime and all of the other stuff fully dynamical, is expected to arise as a result of studying string field theory. Or some other approaches. But what's perhaps important to note is that the dynamics of this 11-dimensional space in which you embed all of the branes definitely also needs to be specified. So where do I place string theory on this? So I branded it as M theory here, and I've placed it in the continuum camp. Because while there definitely is some like discrete numbers labeling a lot of different sectors, those are topological data of continuum manifolds. So for example, in going from 10-dimensional spacetimes to 4-dimensional ones, you have to compactify 6 dimensions. And you always need to compactify on a 6-dimensional continuous manifold. So it's definitely, this is like some of the stuff that definitely is continuous. But as Babs just noted, unless it's something like matrix models or these anti-zero branes, then you might have something discrete, something like non-commutative geometry and fuzzy spheres. That, I think, does go more in the direction of discretization, particularly the fuzzy spheres stuff and non-commutative geometry. And also the matrix models actually goes pretty much in the direction of what group field theories do. It's pretty much, you can think of group field theories as just a generalization of matrix models, which have like infinitely many indices instead of just 2. And yeah, so I place it on the expansive end of the spectrum because I don't think it could deviate further from GR by itself. It has infinitely many more fields, and as far as I'm aware, it's not even it's not optional to have those extra fields. They are part of the package. So you kind of cannot have just GR as a subset of string theory unless you somehow find a sector where all of the other fields are negligible in some way. So it's definitely, it deviates from GR as much as you can possibly think in terms of additional degrees of freedom and phenomena. The next thing I want to, so Bub says you can turn off the fluxes of the compactification, for example, to kill off most of these additional degrees of freedom. Okay, most of them. Now, the next piece I want to get into is asymptotically safe quantum gravity. That's basically the thing I mentioned before in the regulator section. You apply a functional renormalization group to GR, for example, in the Einstein-Hilbert form. And you find that if you overcome the technical questions, which technical questions, okay, I mean, I haven't really written it like this for the other ones. So let me write it like, you choose a diffeomorphism invariant regulator for the gravitational path integral. And then you get flow equations for the couplings for the gravitational coupling and the cosmological constant. And what you find is that in the limit of mu, which is like energy, so to say, if you take this to infinity, then g and lambda take finite values. In terms of what this means in field theory calculations, this entails that you can find a theory at arbitrarily high energies, which is well described by GR plus these extra terms, and which, if you do a Wilsonian IRG flow from it to low energies, then you get back precisely what you find in the classical world. So in principle, what this allows you to do is it allows you to define Einstein-Hilbert action plus some extra stuff, some important extensions, as a theory that works through RG flow from the IR all the way to the UV. And you can then also calculate all of the continuum quantities like graviton propagators and spectral dimensions and such and such and such, area and so forth, by using operator flow equations and evaluating them in the path integral this way. So this can give you a Q of t description of GR. So Q of t in the sense that you have field theories and path integrals. But for quantum gravity. So it will be a Q of t of metrics all the way to all energies. So not Q of t in the sense of you have a free theory, you do perturbations, but Q of t, you have a path integral and you have some flow of couplings, which tells you the effective path integral at all energies. And having the full flow of all of these path integrals gives you the full theory. Next, all right, where do I place this on the scope? I place this very near the conservative end because it's a method that you can apply as a standard thing to basically all QFTs. So the methodology is not that crazy. And it's also fairly continuum in that you basically just work with continuum metrics all the time, and also can include continuum fields on the spacetime. Of course, the same questions of QG still apply. You need to somehow find observables that you can calculate in a way that those observables are diff invariant. So it has the same issues as the ADM formalism, but it approaches it from a continuum path integral side. Now, the next one is causal dynamical triangulations. This is also a path integral approach, but it's a discrete one. So this is a discrete, globally hyperbolic 3 plus 1D path integral approach. Okay, let's say D plus 1D. So what does discrete mean? It means you fix edge lengths and make the spatial slice an arbitrary graph with dynamical topology. Then there are some evolution rules. Which, as far as I remember, are called the 1-5 rule and the 2-3 rule. Or I think 1-4. I think it's 1-4 and 2-3, yes. Yes, because it has to be 5 in total. And then what you can do is you can run numerical simulations, studies. This is something that few quantum gravity approaches can do, which is why a lot of work has gone into this numerical stuff. And it's very interesting because you can, because while there are not that many global observables that have been studied so far, because it's just difficult to find them, you can calculate them to very nice precision. Behavior of, say, the space-time volume, or the of volume, of the spectral dimension, the Hausdorff dimension, and so forth. Those kinds of things have been studied. And in particular, what one finds is a sort of phase diagram for space-times, for QG, which is sort of really like a phase diagram of statistical physics. You have some coupling kappa, and you have some coupling lambda, and then you have a sort of I don't remember actually what it looks like. It's like you have a bifurcation into a bunch of phases, and in one of these phases you get something like de Sitter space. So this is the sort of stuff that you can do in this approach. So this obviously is very discrete. I've placed it pretty much near the top in that it's discrete purely, and there's basically no mention of continuum stuff at all. And there's also not that many attempts to connect it to that, at least not so obviously, so rigorously, let's say. The obvious point, of course, is you just refine the graph far enough that you get something which looks continuous. I also placed it to be relatively conservative because it still has only globally hyperbolic topologies, but it does include stuff like dynamical space-time dimensions and so forth. Now, let's get to the second to last stuff. This is causal sets. Causal sets is a bit of an outlier in all of these approaches in that it doesn't really look like a QG approach per se. Instead, what it does is it reconstructs space-time purely from the causal structure. But particularly from causal relations. So what a causal set is a sort of discrete space-time of chains of events. So it's a sort of a set, and it has an ordering inequality on it, which tells you like which set can influence which. And then there are some, again, some rules which allow you to take a causal set and extend it in a way that looks like an evolution rule. In particular, there is a notion of breaks, which allow you to tell how a causal set becomes more and more continuous. And there are also, of course, some definitions on how to say that a causal set approximates some continuum limit. And there's also some ways to just introduce discretely moving matter, so matter that moves on a graph. Now, I place this very far into the expansive list, not because it includes a lot of degrees of freedom, but mostly because it completely gets rid of the notion of spacetime that we are usually used to, in that you can speak of events as independent of other events. Rather, all you have is really the notion of spacetime as events influencing other events. So you can no longer speak of the field value at a point, because there are no points. There are really no events whatsoever. The only thing you have is really the relation between events. And that makes it very difficult to speak in the same concepts as in GR. In fact, that's also why it's so difficult to match with GR in many situations. I also place it very far in the discrete data direction. I would put it further up, but I cannot, for obvious reasons, I think. Now, there's also modified gravity and higher derivative gravity. I won't say too much about these. Basically, anything that is still sort of seen as an EFT, or maybe again via renormalisation group running, it can be also defined to all energies. Of some theory of metrics, torsion, non-metricity, of dilatons, of vectors, etc., etc. So in principle, you can look for different things here. You can look at different symmetries. For example, conformal gravity, or you can look at something which has only time slice preserving diffeos, which is a very important theory known as Horsava-Lifshitz gravity. If you take anything away from this talk today, it's that you should look up Horsava-Lifshitz gravity. Or, also okay, you can look at renormalizable theories. Gravities. Something like stellar gravity. So I would say if you do anything after today's talk that has to do with QG and you're fully sick of it, look up Horsava-Lifshitz gravity and stellar gravity. Stellar gravity is known as the sort of simplest extension of Einstein-Hilbert that includes an R² term, and which is known to be renormalizable. So it's not renormalizable in this sort of very naive sense, but if you just do a bunch of calculations and define things right, then you can check. You can actually do you can do a theory with finitely many counter terms. So you can do a QFT with this. Of course, it's not GR. If we did live in a world where stellar gravity was accurate to the real world, then we would just use this. There is still some leeway with respect to how accurately stellar gravity can fit to the world, but this is really a separate discussion. Hojava-Lifshitz gravity, on the other end, is also known to have not as many issues as GR because it has a different symmetry group, and it's known to also be renormalizable if you include enough horrible non-covariant higher order terms. Also, and this is perhaps most interesting, if you sort of look at what a few of these approaches have in common or seem to lead to, then you find a sort of congruence between them. So there seems to be a connective square or rectangle between asymptotic safety, causal dynamical triangulations, Hojava-Lifshitz, and stellar gravity. What I mean by this is the following. You can do the asymptotic safety analysis on GR and extend it by operators. And what you find is that the kind of smallest theory space that you can work with is that of stellar gravity. And in that theory space, you actually find something that is well defined to all energies. Now, similarly, you can do sort of matching with continuum theories and the phase diagrams of CDT and of Hojava-Lifshitz gravity. But it's also known that asymptotic safety and causal dynamical triangulations also have a lot of similarities. In particular, the sort of reduced space-time dimensions at high energy scales. So it seems that for some reason, which is really not well understood at this point, there are some correspondences between these different approaches which seem to hint at that maybe in some regimes or in some ways they are actually different versions of the same theory. Particularly where it's not so clear is on the classical level, of course, but also the relations between the other relations are not so clear. Overall, like all of this is very wonky, but it's clear that large results from different approaches already seem to converge to at least a few similar aspects. That's where do I want to place modified gravities of theories of gravity? I don't know. They're still continuum by all means. And in principle, they can be as expansive and conservative as you want. So I just kind of place them in the middle here. But really, it depends on what you look at. If you want to have modified theories of gravity which have infinitely many more particles, then those are, of course, more expansive than the rest. So, yes, this continues the quick survey through, okay, not so quick survey through the QG compass. Hope you enjoyed that. Now we can go on to some Q&A, to some final discussion. I remember a few. I remember one question from earlier. I'll just start with that, and you all can get your questions ready if you want. Okay, what is the most reliable thing we can base a universal time period off of? What is the most reliable method for measuring the speed of light? Okay, the last part does not really like, that is like not related to QG. But the universal time period, that's interesting in that by pure GR alone, the only thing we have is the universe's volume. In principle, I think this would be the simplest answer. If you look at the universe as a whole, then you see it's expanding, and you can use this as a measure of time. All right. Yes. So, are there topics for a Q&A session? Or, I mean, we can also just stop the recording before that, if anyone feels uncomfortable. And if there's no Q&A yet, then I guess we can just stop the recording. Okay, teach me FRG. Okay, FRG, yeah, actually, why not? Why not? Let's do let's do a bit of FRG. I'm gonna have to do this without looking at my notes, so I can so that I can be it can be incredibly cool and totally not wrong in everything I say. So FRG. How does FRG work? So the typical starting point is that you have some sort of path integral generating function. So I don't know, you have some action, some bare action for the fields, and you have some sources, and this gives you a generating functional. And then what you do is you do a Legendre transform. Okay, first you write this as the effective action, right? Right. Ah, no, wait. First it's the generating functional. Yes, now I remember. So first you write this as an exponential here. This W here is the generating functional of connected correlation functions. Then what you can do is you can Legendre transform W via a variable phi, and this gives you the conjugate quantum effective action. So this is called the quantum effective action because it includes, it's the sort of equivalent classical action that includes all of the quantum effects, all of the quantum corrections. Now, what you can do is you can modify. So in principle, this thing here is not well defined because all path integrals are not well defined unless you regulate them. So what you can do is you can modify Z by a regulator, which is scale dependent. So the scale will usually have like momentum dimension 1 or something, or energy dimension 1. And something that you can think of schematically is that you get this effective, is this regulated Z. You still integrate over the same thing. You now integrate over the same action, still with sources, but also you integrate with, you have some extra regulator, some regulating operator here. And the idea is that you have some kind of regulator function. For example, let's say this is about momentum. This is about momentum. And then we require that the only thing that we integrate in this stuff is, okay, now I need to be careful about how I write this. So the point is, let me write this in a separate line. Idea is zk has only integration over degrees of freedom with energy greater than k. So that's the idea. So somehow you have some kind of indicator function cutoff which basically should go like this, in that below k it's basically 0, and at high energies it's basically 1, and it just sort of interpolates between that. So what you do is you introduce a sort of set of regulated path integrals which integrate out all of the higher energies. And what this leads to is a family of effective actions because you can just take zk and write it as eiwk and so forth. And then you can write the full thing as integrating over the fields phi where the momentum is smaller than k with the same action, but rather, okay, it's not the same action, but actually it's the effective action. So what you do sort of is you split the full integration over all the fields into a high energy part and a low energy part. The split is at momentum k. You integrate out all the high energy stuff and you get a low energy path integral with a more complicated action. And then you use this to derive functional RG flow for couplings with respect to K. So you get some better functions of couplings which go like K dGi by dk, and those are usually related to some expectation values, and which also depend on the momentum scale K. Then overall you get recursive relations. And you get also a certain limit. So the limit where K goes to 0 is where your path integral contains all of the modes. This gives you the full path integral. So in principle then, you can see this whole setup as an ODE for Z, K, and you require that the limit ZK, K to 0 exists. Then the theory is well defined to all energies. Be right back. Okay, I'm back. Yes, so the idea is that if you have this this scale-dependent partition function, and you have a differential equation for it, just from formal considerations, then you have an ODE, and if you can solve that ODE with a finite limit in the end, then you have a full theory. That's the idea here. And these functional RG equations lead to what is known as the Wetterich equation. So for interpretation, just some picture. So say we are in we make an ansatz for the effective action as sort of 1 over G Einstein-Hilbert. So here there's lambda over G, and then we have some additional term rho with r squared. So we're in the theory space of static gravity. Then it's known, for example, that you can have a flow in the space of couplings, which sort of like spirals in on a UV fixed point. So from the UV, we get a set of effective theories at lower and lower energies, which we can trace back as coming from a special point in the UV, where the special point has finite values of the couplings. So by this measure, so of course I'm not plotting the whole thing here, like there's also some value for the coupling rho. In principle then, if you have the full RG flow, then you can calculate quantities at all energies. So in that sense, it's a full theory to all energies, particularly because the couplings are all finite, and the theory is regulated. Unless you're doing something wrong, then the theories, like quantities, will also all be finite. Apart from, of course, I like the issues like IR stuff and so forth. Do you have questions, Bubs? Not specific ones. That's good. All right. I didn't see other questions pop up so far. So maybe this is a good point to stop and just, yeah, wrap up for this session and possibly the series. I don't know if I'm going to continue. All right, I'll stop the recording.